Okay, so it's my pleasure to present to you today a brief presentation on our paper entitled Heavy Duty Fuel Systems Developing the Next Generation on behalf of Delphi Powertrain Systems Commercial Vehicle FIE. Before I start, I'd like to thank my colleagues and co-authors for their help. Okay, so first of all, let's start with a company overview. So Delphi Powertrain Systems Commercial Vehicle FIE manufactures fuel systems for a full range of commercial vehicles. We have 3 sites across the UK and we employ approximately 2,000 employees. Delphi has been supplying heavy-duty injectors and unit pumps for the past 2 decades. We started series production of 3 unique heavy-duty common rail systems in 2012. So some of our customer drivers. So customer driver, what customer wants? We want efficiency, CO2, so fuel economy, noise, vibration, harshness, consistency over life, and support for a range of combustion strategies, and also not forgetting the current emission legislation. So technology drivers, what we have to achieve to maintain these. So we need multiple injection control, we need a rate shape controllability, we need pressure capability, and we need parasitic leakage to a near zero level. We also need robustness to fuel quality and fueling consistency over life, and also we need good integration of the FIE within the engine architecture itself. So here's a quick overview of the future system. So showing a remote pump with modular pump, a remote cam box with modular pumps, the high pressure common rail, the injector itself, and the ECU. And today we're going to focus on the core technology inside our injector. So at the core of our heavy duty injector is the actuator assembly itself. It's made up of a solenoid through-way control valve. The solenoid stator provides a cost-effective and durable means of driving the control valve. The 3-way valve controls the volume of pressurized fuel behind the nozzle needle. So you can see here. Benefits of using a 3-way type valve are a near zero total drive cycle leakage, which improves system efficiency. Actuation characteristics that remain consistent over life and operating pressures and multiple injection range. The actuator assembly indirectly and hydraulically controls the nozzle assembly. This nozzle assembly consists of a needle operating in a high pressure reservoir. Actuator control of the volume above the nozzle needle indirectly controls its motion, which allows for complex and fine-tuned injection rate shapes. So the next few slides will give a simple injection cycle. So first, the key features to point out are a source of high pressure fuel in the system, typically a common rail. The solenoid stator, which acts as a spring-loaded nozzle control valve. The NCV is a 3-way valve that controls a spring-loaded nozzle. And the nozzle contains a needle valve, which the NCV controls by filling and draining the volume above it. So the cycle itself. At rest, the spring-loaded NCV seals the drain path and prevents high pressure from escaping. The high pressure fuel fills the volume above the nozzle needle and holds it on its seat here. So no injection can occur. When the NCV is actuated by the solenoid, it moves upwards, opening this drain path, and the volume of pressurized fuel above the nozzle needle is allowed to drain and allowing the nozzle needle to lift, thus beginning injection. The NCV continues to be actuated and nozzle needle held open for the duration required to get the targeted injected fuel quantity. To stop injection, the NCV ceases to be actuated and begins to seal the drain path again. This in turn diverts high pressure fuel to the back or the top of the nozzle needle, moving it toward the seat and sealing the flow path. The NCV and nozzle needle are now at rest here, and high pressure fuel is sealed and injection has ceased. So, moving on to component miniaturization. So the fundamental achievement in this method of injection cycle is the miniaturization of the components within the DFI-21, which are key to improving quicker control, response, and achieving complex injection capability. In order to maintain robustness and durability, materials, geometry, and manufacturing processes are optimized throughout the design and development stages. So the DFA-21 features a miniaturized actuator assembly which provides 3 key advantages, which are greater system efficiency, complex injection capability, and external packaging flexibility. This following chart will summarize this. So a smaller componentry reduces the inertia exerted during the valve switching. Smaller componentry decreases the size of the feed paths required for actuation, and therefore the quantity of hydraulic volume lost during valve switching, which is termed dynamic leakage. Reducing the size of feed paths also restricts the static leakage paths associated with a three-way valve. This allows for greater system efficiency. A smaller actuator assembly enables a much smaller overall injector unit. This allows for a greater range of freedom when locating the injector within the engine layout itself. There's also a greater freedom of packaging within the injector itself, allowing for optimal routing of high pressure drillings to maximize nozzle volume, which will both greatly improve internal hydraulic interaction. A smaller actuator also only has to deal with far lower hydraulic forces acting on it. Because of this and a lower switching inertia, the electromagnetic force required is much lower, and therefore only demands a smaller stator. A smaller stator allows for faster flux build and decay, which produces characteristics comparable to that of piezo actuators. This, coupled with optimized hydraulic interaction, provides a faster magnetic and mechanical response than that of the hydraulic circuit. The result is the ability to perform complex injections such as steeper rate shapes and close-coupled multiple injections. So as I've just mentioned, one of the significant merits of the DFI-21 is its greater system efficiency, which I will go into in more detail. Okay, so minimize leakage. Here we demonstrate how to minimize, how miniaturization reduces static and dynamic leakage in a three-way valve. Dynamic leakage is due to fuel flow through the control chamber when the NCV pin and nozzle needle are moving. So you see here, the pin is moving upwards and flow of fuel. Reducing the size of the NCV and therefore the travel of the NCV pin, this minimizes the time when fluid can flow from the low to high pressure. Once the NCV pin and needle are on their top seats, the high and low pressure circuits are sealed again. So reducing the size of the control chambers results in less high pressure fuel being drained into the low pressure circuit. Reduction in NCV pin diameter means a smaller flow area for fuel to leak from high to low pressure chambers, therefore reducing static leakage. So you see reducing these diameters here and here. We move on to some leakage results. Okay, here you can see a graph showing from 1 to 6 injection events, showing a total drive cycle leakage. Miniaturization has made significant reductions in leakage to a near zero level. Data shows a significant improvement from the current Euro 6 FIE. Big data shows up to 80% reduction in total drive cycle leakage. Another significant merit of the DFI-21 is its complex injection capability. With the accuracy of Delphi's three-way control valve and nozzle damping characteristics, allow the rate of injection to be manipulated to suit different combustion strategy. Here are just some examples of some typical rate shapes we see. Square rate trace supports an EGR-based combustion strategy. So this maintains a high mean injection pressure, which aids in reducing the compromise on particulates associated with the EGR strategy. And the SCR strategy benefits from a lower average rate of pressure and a re-optimization of the injection rate trace, which to produce a slower start of rate slope. And this rising rate shape helps to reduce the instantaneous rate of heat release and NOx formation at the initial stage of the combustion event. So this graph shows some performance rig data with nozzle flow rates at a 1200 bar rail pressure. So each of the traces is achieved by a variation of a designed in-production variant. This allows the injector to be suitable for a wide range of engine types and combustion strategies. The DFI-21 injector demonstrates an inherent versatility in design, allowing for this simple manipulation of the flow rate through the nozzle. So this in turn gives us more consistency, shot to shot, unit to unit, and due to the reduced effects of pressure waves. This benefit enables the injector to be applied to an EGR-only strategy, an SCR-only strategy, or a combination of both, depending on the customer requirements. This is due to the independence we have between our starting rate and our end rate. That's multiple injection. Miniaturization creates short flow paths and small control volumes, which leads to rapid and consistent actuations, as I've just previously mentioned. This in turn allows for the use of high frequency multiple injections, as you can see here. The above example showed 9 injections within a 3 microsecond time span. The consistency of one injection to the next shows that there is minimal electromagnetic or pressure wave effects. The increase in injection size changes consistently with pressure from 400 to 2400 bar, as you can see here. This allows effective performance prediction and accurate extrapolation across the fueling map for even the most complex injection events, which we have demonstrated with injection separations as low as 100 microseconds. Here we move on to some multi-cylinder multiple injection results. So here you can see the multiple injection results from a multi-cylinder engine that we have in Park Royal. The plot on the left is at a constant NOx level, showing injection events, 1 to 6 injection events. In the green we have noise, okay, sorry, it's a bit hard to see, in decibels. In the blue we have soot in milligrams per kilowatt hour, and in the red we have BSFC. So on the right you will see a single injection event showing 6 overlaid heat release curves calculated from individual cylinder pressures and given the resultant values here and here for noise, soot and BSFC. The addition of 3 pilot injections dramatically reduces noise from here all the way down to here, with a slight reduction in BSFC from here to here, but there is a soot penalty for this. So to combat this, further addition of 2 post injections. So the further addition of 2 post injections are used to oxidize the remaining soot in the cylinder, drastically reducing this, and further reduce the BSFC here, and still maintain a low combustion noise that we've initially wanted to achieve. From our testing, we have demonstrated up to 2% reduction in BSFC, a 6 decibel reduction in combustion noise, and up to 50% reduction in soot. As well as performance benefits of miniaturization, a smaller injector envelope is more accommodating to package. A small actuator and nozzle assembly provides a modular design that can be easily integrated into future customer engine designs, or as a straightforward upgrade for existing customers using the larger Euro 6 products. This versatility also extends beyond the heavy duty sector and into potential use for the medium and light duty sectors also. Overall, it introduces greater flexibility of injector location within the engine layouts, whilst reducing the need for compromise on other important aspects such as routing of high pressure fuel pipes, etc. Other physical advantages of the DFI-21 are the lower material requirement for manufacture, as well as a lighter overall product that is easier to handle and transport. In addition to the cost benefits, this is inherently has a lower environmental impact. As you can see here, the DFI-21 technology fits and operates in each of these injectors displayed here. So, the DFI-21 gives us great system efficiency, and also gives us the ability to achieve more complex injection, and it gives a greater packaging flexibility. Thank you for your time, and look forward to your questions.